Welcome back. In this segment, we will discuss biomechanics of manual material handling tasks. And material handling is one of the most common tasks that are performed in all organizations, whether they are manufacturing organizations or service organizations. And still, even today, with the advancement in technology, many times these material handling tasks are performed manually. So in this segment, we will analyze such tasks from the point of view of biomechanics. So we will take a simple example of a person who is holding a weight or load, we call it L, in front of his body. And we are focusing here actually on the intervertebral disc somewhere over here. So that will be L4, L5 intervertebral disc. So the distance of this load that is held in front of the body from the center of the backbone, that is sort of center of the disc as well, is small l. The weight of the upper body of this person is W, capital W, and the distance of the weight of upper body from this center point is small w. In order to keep the body in balance, the back muscles have to uh, generate some force as well. So we call that force to be capital M, and the vertical distance of the force generated by these back muscles, for example, maybe these are the erector spinae muscles, is small m. So you know that whenever we are sitting or standing or whenever we are um, handling material, the disc is compressed. Now you can see that all these three forces, the load of the say material that this person is holding, the weight of upper body, as well as the muscle forces are acting downwards. So again, according to Newton's third law, there should be a resistive force, that is the compressive force actually, that is acting on this disc in the upward direction, that is the force C. So these are the forces that are acting on this L4, L5 disc. And of course, the torque because of this compressive force C will be zero at this point because of this forces passing just through the center of this disc. So let's try to develop an equation for this simple situation. But just notice one thing, that we have uh, taken an assumption, and that is we have taken this force to be perpendicular, or we have taken the actually vertical component of this force. We have sort of ignored the horizontal component because actual direction of the force will be this one, because the person is bending in the forward direction. So actual direction of the force will be this one. So this will be making sort of some angle with the vertical. But to make the analysis simple, we have taken the force to be perpendicular, or we have ignored the horizontal component of this force. And we will come to that point at the end of our analysis. So the external load L pulls downward, the upper body weight Wx downward as well. The distances small n and small w are the lever arms of load and weight to the point of support. That is the fulcrum of the system, that is a disc of the spinal column, that is in this case L4, L5 disc. The forces capital L and W exert the moments capital L into small l, that is force into distance, and capital W into small w, that is also force into distance. And you can see that both these forces will have a tendency to create clockwise torque around this point. So the torques of both these forces, L and W, will be clockwise. Now the counteraction comes mostly from the muscle that attach to the spinous processes. That is the projections of the vertebrae that project on the posterior side as well as on the lateral sides. But specifically, we are talking about the muscles that are on the that are attaching to the posterior projections or processes. And together, these muscles produce a force capital M. So this force M uses its lever arm small m to the fulcrum to generate the moment minus m into m. The minus sign indicates the torque is in the direction opposite to the torques due to W and L. So this torque because of this force will be counterclockwise, and because of these two forces will be clockwise. And in order for this person to be in balance, the sum of these clockwise torques should be equal to this counterclockwise torque. The upright force C at the spinal column keeps the system in place in vertical direction. So uh, that is the summary of the situation, the forces that are acting, and the resistive forces, the direction of torques, and the direction of different forces and their moment arms. So when will the system be in balance? So if we use the equation of torque, so as we saw that these two torques are clockwise, and the torques because of this muscle force is counterclockwise. So simply this counterclockwise torque should be equal to the sum of clockwise torques. And similarly, the sum of the forces that are acting downward should be equal to this force C. So L is acting downward, the weight of the upper body is acting downward, and the muscular force is acting downward. So sum of these forces should be equal to this compressive force C. So that is a simple situation to analyze mathematically. So first equation is this one. Sum of uh, clockwise torque should be equal to counterclockwise torque. And if we rearrange, we can write in this form to find this muscle force M. Because the weight of the body and the weight that is being held can be found easily, and we can eventually calculate this muscle force M. And this counter force or compressive force should be equal to sum of the other three forces. So these are the two equations we will be using for the analysis. So assume that external load is 100 newtons and its lever arm is 25 centimeters. The upper body weight W, that is 500 newtons, and its lever arm is 15 centimeters. The lever arm M of the muscle force is 5 centimeters. So what we are given is this load that is being held is 100 newtons. This small L is 25 centimeters. The weight of the upper body is 500 newtons or approximately 50 kilograms. And this small W is 15 centimeters. And this small m, this distance is 5 centimeters. And we have to find this force M. So that is the situation that we are confronting. So we will use the same equations that we just developed to find these forces. So for example, our first equation was Counterclockwise torque should be equal to sum of the clockwise torques. So this M, that is the sum of the forces of back muscles, is unknown, into 5. That will be equal to, that W is 100, its lever arm is 25. So this 125 clockwise torque plus weight of upper body into its moment arm. So that will turn out to be, turns out to be how much? So I hope you are solving. So that is 2000 newtons. So basic idea was that sum of the clockwise torque should be equal to counterclockwise torques. One force that remains is this force C. So we can use the same equation, that sum of upward forces should be equal to sum of downward forces. So this C is acting upwards, so that will be equal to, all other forces are downward, so they are L plus W plus M, so that is 100 plus 500 plus 2000, so that turns out to be 2600 newtons. Now it is very important to see what these values are actually indicating. So this muscle force of 2000 newtons and this force on the disc of 2600 newtons. So in this example, this force, muscle force, that is 2000 newtons, is about 20 times of the load. So load was 100 newtons. And the force, this force M, turns out to be 2000 newtons. So that is 20 times this load. And this C was 2600 newtons. So that is about 26 times the external load, the load of 100 newtons. So what's happening? The basic reason of these two very high forces is small lever arm of this muscle force M. That was 5 centimeters. So of course, smaller is the lever arm, the greater will be the force, and vice versa, in order to keep the system in balance. Now the problem is, this lever arm of force generated by the back muscles is not in our control. This lever is anatomically determined, so we cannot change it. Its position is fixed. The distance of the intervertebral disc from the back muscles is fixed. We cannot change it. But a couple of things are actually in our control. One of them is the load itself, external load. This load of 100 Newton is in our control. And its location from the body is also in our control. So we can decide in many cases what should be the load and what should be its distance from the body. So to reduce the risk to connective spinal tissues and the column, we can draw three simple conclusions. Keep the external load small. So why 100 Newton? Cannot it be reduced? If yes, better. Second, keep the external load close to the body. Why a lever arm of, that was I think 25 centimeters, sorry. Why 25 centimeters? Why can't it be reduced? And thirdly, keep the upper body upright. So this is also a very important point. So at the moment, we will focus on this third point. Keep the body upright. Now, what will be the effect of keeping the body upright? As much straight as possible. What will be the impact? So we will address the third point using the same example. So for example, this person is now having his back straight. Practically, it is not possible in all situations. But the basic point is keep it as straight as possible. So let's go to the other extreme that the posture is perfectly straight. So we keep everything else the same and change the posture only. The person stands erect instead of forward bending, so the statement now becomes the external load is 100 newtons, its lever arm is 25 centimeters, the upper body weight is 500 newtons, with the person standing erect. The lever arm M of the muscle is again the same 5 centimeters. So what will be the effect on disc loading? So let's solve it first and then we will draw a conclusion. So we will solve quickly because most of the things are the same. So we had this simple equation, the counterclockwise torque should be equal to the sum of clockwise torques. But just in order to reiterate and to get your attention, suppose this is the center point of L4, L5 disc. So this load was 100 newtons and this distance was 25 centimeters. Now, what about the weight of the upper body? Weight of the upper body. Now it acts almost exactly at a point that is above this disc. So that was W, and that was 500 newtons. Now its lever arm now becomes almost zero. We are assuming it to be zero because practically the center of gravity might not be exactly at the top of this disc, but we are assuming it to be so. And somewhere over here was force M, capital M, and this distance, this small distance was 5 centimeters. And there was a resistive force as well, so that was acting in the upward direction, so that was force C. So that was the situation. That has slightly changed now. So this M is to be found. This lever arm of 5 is the same. Now the weight of the person is 500, but its lever arm has changed to 0 or very small value practically. Load is 100 and we are assuming its lever arm is still the same, but practically it might reduce as well. So that M turns out to be 500 newtons. Okay. And similarly regarding the force C, so that was C was equal to sum of the forces acting downwards. So you can see this L, W, M, they are all acting downwards. So C will be equal to 100. That is the load being held, 500 the weight of upper body, and M that we just found was 500. So that turns out to be how much? 1100 newtons. So previously this force was how much? This M, 2000 newtons, and this L was 2600 newtons. So by just changing the posture, the force has reduced. This force M, muscle resistive force, has reduced from 2000 to 500 newtons. That is a 75% reduction. And this, sorry, this was C, the compressive force. So this was C. So that has reduced from 2600 to 1100 newtons. So that is a reduction of 58%. So by just changing the posture, both forces, the force developed by the back muscles and the force acting on the disc, both have reduced significantly. Of course, we took some small assumptions in this case as well, but that is quite true that by just improving the posture, a lot of stress on the back muscles and disc and the vertebrae can be reduced. So we will solve a similar example in the next segment as well and try to draw some conclusions there as well. So I hope this concept, biomechanical analysis of the backbone during manual material handling task is clear. If you have any questions, you can ask.